Hi, this is Andrea Hendricks. The topic of this video lesson is logarithmic functions. We're going to talk more about how to graph a logarithmic function, find the domain of those functions, use things we've talked about before involving translations and reflections to graph, and also find the inverse of a log and/or exponential function. So our first objective is to graph a logarithmic function of the form y is equal to log base a of x. So this is going to be one of our basic functions that we add to the set we already know. There are two cases when we have a log function, and that is the base a is either greater than 1 or between 0 and 1. So let's first talk about the graph y is equal to log x. This is the case when the base a is equal to 10. Well, to make a graph, what we would do is just make a chart of values. When we're thinking about log x, we could either think of our input is going to be the result of 10 to some power, right? Because y is equal to log x really means 10 to the y is equal to x. So it might be that you want to put in values for y and then find the x. So for instance, if I put in -2 or -1, 0, 1, and 2, 10 to the -2 would be 1 over 10 squared, or 1 over 100, which is 0.01. Now if we put in -1, 10 to the -1 would be 1 over 10, or 0.1. 10 to the 0 is 1. 10 to the first power is 10, and 10 squared is 100. Now certainly I could have substituted these values in for x, but sometimes that's a little bit harder to think about because the numbers that you plug in to make it easy would need to be perfect powers of the base. For bases of or powers of 10, that's not really too difficult, but it can get tricky if the base is something other than that. So now if we wanted to graph this, let's look at the properties that this graph possesses. So we have, what, 0.01, -2. That's going to be kind of hard to graph. 0.1, -1, 1, 0, and then 10, 1. That's beyond the scope of my graph. We'll just put it over here. Okay, so now if we graph this by connecting these points, we get this graph. A logarithmic function is used primarily to model very slow growth. Right, you can see that because it takes the value of 100 before we even get to a y value of 2. Now, what are some characteristics of this graph? We know that the domain is from 0 to infinity, right? We talked about that 10 to a power can never be 0, nor can it be negative, so our domain has to be from 0 to infinity. The range is bottom up. It's going to be -infinity to infinity. The key point on this graph is a point 1, 0, and it is an increasing continuous function. And there's also a vertical asymptote, and the vertical asymptote is at x is equal to 0. Okay, so hopefully these things are kind of ringing a bell with things we talked about with exponential functions, because these are actually the opposite of everything we talked about with exponential functions. Now let's talk about y is equal to log base 1/2 of x. So what this means here, first off, notice that our base is 1/2. So this means 1/2 to the y is equal to x. So for graphing this, we're definitely going to put in values for y, like -2, -1, 0, 1, and 2, and compute the x value. So 1/2 to the -2, remember when you have a negative exponent, you can take the reciprocal and make the exponent positive. So 1/2 to the -2 would really be 2 squared, or 4. 1/2 to the -1 would be 2 to the first power, or 2. 1/2 to the 0 is 1. 1/2 to the first power is 1/2, and 1/2 squared would be 1/4. Okay, so now when we graph this one, for -2, it's here, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. So connecting these points, we get this graph. And that is because this is actually a reflection. 1/2, remember, is 2 to the -1, right? So this is like 2 to the -y is equal to x. So this is a reflection of the log base 2 of x across the x-axis. So notice some really similarities and a few changes. The domain is still 0 to infinity, right? The range is -infinity to infinity. There's still a vertical asymptote at x equals 0. Our key point is still 1, 0. And this time we have a graph that is decreasing. Okay? So if the base is between 0 and 1, you're going to have a decreasing function. If it's greater than 1, you're going to have an increasing function. Other than that, a lot of the properties are the same. Now, let me back up and remind you that on the calculator, you can only graph the common log and the natural log with those functions that are built in. If you want to graph log 1/2 x, you're going to have to use the change of base formula, and just recall the change of base formula says that the log base 1/2 of x is equivalent to the common log of x over the common log of 1/2. Remember, the base has to go in the basement. Now, I could have also used natural log. I could have written this as the natural log of x over the natural log of 1/2. But that's the way I would have to input it on the calculator to get the calculator to draw the graph for me. Now, let's talk about the domain of a log function. The key idea is that the input of the log must be positive. So to find the domain, we have to set the expression in the log function greater than 0 and solve. It's kind of like those root functions where we had an even index. We had to set the expression inside greater than or equal to 0. Well, here we just have to set it greater than 0 because we can't have an input of 0 because there's no base to power that gives us 0 for those exponential functions that we've talked about. So if I wanted to find the domain of y is equal to the log base 2 of x plus 3, what I'm going to do is set x plus 3 to be greater than 0 and solve that. So x would be greater than -3. So my domain is from -3 to infinity. If I have the log base 5 of 4 minus x, I would set 4 minus x to be greater than 0. So that would mean -x has to be greater than -4. And then I have to divide through by -1, which will reverse the inequality symbol to be x is less than 4. So that one would be from -infinity to 4. Now the last one is log x plus 3. Well, here The only input in the log is the x because the 3 is not connected with parentheses. So here we just simply say that x has to be greater than 0. So our domain would be from 0 to infinity. And the last problem, y is equal to the natural log of x squared minus 9. So to solve this problem for the domain, I have to find where x squared minus 9 is greater than 0. Well, this is a quadratic inequality. So to solve a quadratic inequality, do you remember you have to set it equal to 0 and then test points or either use the calculator to determine the regions that test true. But if I solve this, I would get x squared equals 9, so x would be plus or minus the square root of 9, which is plus or minus 3. And then we could test points in each of those intervals, or we can use the fact that x squared minus 9 is a parabola that opens up. It goes through the x-intercepts of negative 3 and 3. So it's greater than 0 where it's above the x-axis, which is to the left of negative 3 and to the right of 3. And so that graph tells me that the solution would be on those outside regions. I cannot include the endpoint because I can't allow it to be equal to 0, so I would have parentheses. So my domain is from negative infinity to negative 3, union 3 to infinity. Now if you don't like using the parabola, you could plug in a point like negative 4. Negative 4 squared is positive 16, minus 9 is 7, which is greater than 0, so that checks. And then plug 1 for each of those other regions. Now, let's use reflections and translations to graph the log functions. If I have y is equal to the log of x plus 2, so I'm thinking of the key function as just the log x and those properties we discussed earlier. So this would be a shifting of what? Yeah, the change is attached to x, so that's going to shift it horizontally, right, left or right. If we're adding, it actually shifts it in the opposite direction. So we're going to get a shift left 2 units. So that basic log function had a vertical asymptote at x equals 0, so we've got to shift it left 2 units, which would take it to negative 2. Our key point was at 1, 0, shifting left 2 would take us to negative 1, 0, and then we know the basic shape. Model slow growth, so it looks like that. So the domain is from negative 2 to infinity. The range is from negative infinity to infinity. We have a vertical asymptote at x equals negative 2, and the point goes through negative 1, 0. Now how does y equals log x minus 2 compare? Well, that one now we're subtracting 2 from the log function, so this one is a shifting down 2 units. And so if we have a vertical asymptote at x equals 0, to shift it down 2 units still stays at x equals 0. We haven't affected the domain. Our key point of 1, 0 now goes down 2 units to be 1, negative 2. And there we go. So the domain is from 0 to infinity. The range is from negative infinity to infinity. And the vertical asymptote is x equals 0. Now what about y is equal to the log of negative x? Okay, involving a negative involves reflections, right? And when the x is taken to be the opposite of, that's going to be a reflection across the y-axis, right? So to reflect across the y means we're going to do the opposite of x and keep y the same. Well, that is from the original graph that we had. So our vertical asymptote is not going to change. It's still going to be at x equals 0. Our key point of 1, 0, though, will be reflected. It's going to be reflected to the point of -1, 0. Okay. And remember, it was going like this, but to do the reflection, it's going to go like this. So now our domain is from -infinity to 0. The range is unchanged. And our vertical asymptote is unchanged. Okay. Now, the last concept we need to talk about is finding the inverse of a log or exponential function. And do you remember to find the inverse? That's where we have to interchange the x and the y and solve for the y. So if we wanted to find the inverse of y is equal to the log base 2 of x, the first thing I would need to do is convert that to the equivalent exponential form. This is equivalent to 2 to the y is equal to x. So that is just the exponential form of that log function. Now I've got to interchange my x and y. And now I've got to solve for y. Well, I've actually already solved for y with interchanging, so y is equal to 2 to the x is the inverse of log base 2 of x. So f inverse of x is 2 to the x. So the inverse of a log is an exponential function. And do you remember the graph? We can look at that real quickly. Log base 2 of x is that one that we just talked about. That goes to the point 1, 0 and has a vertical asymptote. Well, 2 to the x goes through 0, 1, right? And has a horizontal asymptote. And do you remember the properties of exponential or inverse functions rather? They have to be a reflection about the line y is equal to x. And they are in this case. And we'll talk about checking the compositions of the function and the inverse in just a minute. So let's look at one more example. If we have y is equal to 4 to the x minus 3, in this case we would need to think about changing the x and the y. So we're going to have x now is equal to 4 to the y minus 3. And now we need to solve for the y. So to solve for y, we need to get 4 to the y on the side by itself. So we would have x minus 3, x plus 3 rather, is equal to 4 to the y. So to solve for y, we need to think about how we can bring the y down from the exponent. Well, we could use the log function, and if we take the log base 4 of both sides, and I chose to do base 4 because my base of my exponent was 4. Well, remember that key property we talked about, log base 4, 4 to the y, simply y, or the exponent also comes down, however you want to think of that. And then on the other side we get log base 4 of x plus 3. Okay? Now think about graphically what that means just to see that they are reflections. So this would be the inverse function. 4 to the x minus 3 would have a horizontal asymptote at -3. And that point 0, 1 is going to go down 3 units. Okay. Now log base 4 of x plus 3 is going to shift left 3 units. And our key point of 1, 0 is going to go left 3 units. Okay. And then you could look at the fact that they are symmetric about the line y is equal to x. Okay. Now we can also see that with compositions. If I say f of x is equal to 4 to the x minus 3, and f inverse of x is equal to the log base 4 of x plus 3. To verify that two functions are compositions, we have to do f composed with f inverse of x and see that we get x. So let's just do that one way. You also have to do the other composition, but we'll just do this one way. If we do f of f inverse, we'd have to do f of log base 4 of x plus 3. And remember that now we're going to plug in this expression into the function f in place of x. So this would become 4 to the log base 4 of x plus 3, and then minus 3. We talked about this property on another video. When the bases are the same and the exponent and the log, those cancel each other out to just give us what's inside the log. So this would just be x plus 3 minus 3, which is simply x. So that's confirmed. And then you could do the other composition, f inverse composed with f of x, to also see that you get x. Okay? So we talked about a lot: graphing, finding the domain, using shiftings and reflections, and then also finding the inverses. So if you have any questions, don't hesitate to contact me. Thanks.